Okay, class activity 5A is about building a buck converter to convert between this 100-volt source down to a 25-volt source. And you can see that we're going to use this PWM frequency, and then we want a ripple of 2.5 volts with a power of 1 kilowatt. So first of all, we need to figure out what the value is for our resistor. So we're just going to say that P equals V squared over R. So we get 1,000 equals 25 squared over R. So we solve this and get an R of 0.625. Okay, so the next thing we need to do is to figure out our duty cycle. So the duty cycle is just going to be equal to 25 over 100, which is equal to 0.25 or 25%. And our frequency, our time period is going to be 10 to the minus 4, which is 100 microseconds. Okay, so then we want to look at our basic circuit. So here's what our basic circuit is going to look like. We have a switch, and then we have another switch, we have an inductor, and a resistor like that. And then this is 100 volts. This is 0.625. So then what we're going to do is we are going to convert this switch right here into a diode and this switch right there into a MOSFET. Now, there's two different ways that we can do with the MOSFET. We can do the MOSFET as a PMOS or as an NMOS. So we're going to start with it with a PMOS. So here is our PMOS. Then here is our diode, and then this goes over to the inductor, and the resistor looks like that. So this is 100 volts, and this is 0.625. Now we need the value for our inductor. So we could go back to what we derived before, or we kind of grab the book and look for the base equation. So here is our base equation. This one is using little delta instead of D for the duty cycle. So here is our current equation right here. V over L times T times D minus D squared. Okay, and we are after ripple, so delta V is equal to delta I times RL, which is going to be equal to V times RL over L times T times D minus D squared. Okay, so then this is going to be equal to 100 times 0.625 over L times 10 to the minus 4 times 0.25 minus 0.25 squared. And this should be equal to, we were shooting for a peak-to-peak ripple of 2.5. Okay, so then we go and solve that. And so we solve that and we get L is equal to 0.46, well, we're just going to have to round it, 4.7 millihenries. Okay, so now we're ready to go to LTspice to get all this to work out. So let's open LTspice. And build our basic circuit. So we're going to start with our load resistor. and it's going to be 0.625 ohms. And let's go ahead and put an output node on there. Okay, and then we're going to add in our inductor. And that inductor is supposed to be 0.47 millihenries. Okay, and then we're going to throw our diode on first. And it is going to have current flow this direction. Now we have to go find a diode. This is going to be 100 volts, so we want the breakdown greater than 100 volts, and we're going to be driving fairly high current. So we want to get a diode that can handle the high current. So they only have diodes that go up to 30 amps, so we'll just use one of those. Go ahead and use a fast recovery one. Any of these through here would work. So we'll just grab this one here. Good enough. Okay, so we're going to start this by getting a PMOS. And remember that the current flows for PMOS from the source to the drain, so it has to be oriented this direction. Okay, we're going to add a voltage source. Let's call this VDC, and we have 100 volts. Okay, now we have to get a PMOS. Now our PMOS, again, has to have a voltage greater around 100 volts. We want our on to be fairly small, and we want the gate charge, which is how fast it's going to switch, to be fairly small. So it's kind of a trade-off here. So here's one with an R, small R on and a small gate charge. Let's just go ahead and grab that one. Okay, so now we have to be able to switch this. Well, the source is going up and down, since we're on the high side, and this is 100 volts, and so let's start by looking at our gate driver. So the gate driver that we were using was the LTC1693. Well, that didn't seem to work. LTC. Okay. And so we look at this, and we're looking at the maximum values. So you see that the maximum supply voltage that it can take is 13 volts. So that's not going to work for this because we're trying to switch to 100 volts. So the first thing that we're going to do is just go back to just use our standard levels shifter that we had before. So we're going to grab an NMOS to do that. Now before we were using the 2N7002, but you see it only goes up to 60 volts. So we don't want to use that one. We need one that can handle switching 100 volts. So we're going to get 100 volts. And again, we want this to switch fast. So we're primarily concerned about the gate charge. So might as well pick a really small one like this, as a gate charge of 1 nanocoulomb, really small. So we're going to grab this one as our level shifter. Okay, so then we're going to put over here our pulse voltage. Now we want, this is going to be, so you see our source is 100 volts and we want our gate voltage to be switching up to 80. So we're going to want the voltage at this point to be changing from 80 to 100. So not from 100 all the way to 0. So we're going to have to take the 100 volts and voltage divide it down. So we need to drop it down. So if I use a 1K and a 3K and a 4K, then that's going to switch it down. And we're going to put a resistor here to limit the current flow of our controller. So let's pick 500, should be good. Okay, now if I look right here, we're going to build the pulse, and then this one, when this voltage is high, this transistor turns on and this goes down. So a high voltage here produces a low voltage here, okay? And a low voltage here is going to turn on this transistor, which pulls that high, okay? To go through all of that, to walk through that process. Because we have to watch whether it's inverted or non-inverted. Now, the problem we run into here is right here, it's going to be pulling through these different resistors, and we're trying to get a high voltage spike. So we're going to add a new component in here that's some type of gate driver. So if I type in you see that here is an example of a gate driver. Now, this gate driver is officially called, I think it's called a totem pole gate driver. And so what you see here is we're taking two BJTs, but we're connecting the base to emitter of the two together. So you see, if I'm talking at my input right here, oh, then I'm going to have this 0.7 volt drop across here. Or if this voltage is low, I get 0.7 volt drop up there. But the current is getting pulled through here, not through there. So we're going to use this totem pole gate driver configuration. So we're going to break this line. And we're going to grab an NPN. And we're going to grab a PNP. And then this one we have to flip around. So that the two emitters are connected together. This ties up to here. This is going to tie down to ground. Let's make this a little bigger. Okay, so let's go grab these MOSFETs, or no, the BJT. And again, we can't use the standard one because they're too small. I need one that can handle the 120 volts. So we'll just grab this first one here. Grab the PNP, do the same thing. Grab the first one there. Okay, so now this is going to be 0 or 100 volts. And so this point here is going to be either 100 volts minus 0.7 or 0 volts plus 0.7. So it'll be a little bit different than the 80. We could adjust this a little bit to compensate for that, but 19.3 should be good enough to get all this to work. Okay, so now we're going to come in here and we're going to do our pulse. So we're going to go from 0 to 3.3 volts, no delay. We're going to do small rise and fall time. We want 0.25, I guess we'll do 25 micro and 100 micro to get our 20 kilohertz switching. Okay, so now let's run this and see how it looks. So I run this, and we look right here. Here we're going up and down between that, and then if I go over here, you see this is my 80 to 100. I look right here, here is my 80 to 100. I look right here, here is my 80 to 100. Or now this one's going from 0 to 100 volts. And I look right here and it's kind of going up, but I haven't gotten to steady state. So I got to go a lot longer because the inductor takes time to charge up. So we're going to go to 10 milli, do like 9.5 milli because I don't want to see all of them. Okay, and then we're going up and down and up and down, and everything's looking like this. So let's see how close we got. So you see we have a ripple of 2.55. We could adjust that just a little bit if we wanted to get it to exactly 2.5. And if I look at my average voltage, I'm at 24.15. We wanted 25. Now, when you do the average up here, you got to make sure that you have an even number of periods. And so that's why we have 100 micro, so 9.5 is an even 5 periods. So we can increase that a little bit if we wanted to get a little closer. And there's our 25.1. Okay, so let's look at how all this works really quick. So if I go and look at this current, you see I'm getting these current spikes that are getting up to 350 or 200 milliamps, where if let's see what would have happened if I would have just connected these straight together. Let's get around that transistor. Okay. So you see these are only going up to 20 milliamps because of these kilo ohm resistors. So this gate driver takes the 20 milliamps and gives it the current spikes that it needs in order to be more efficient. So let's go back to where we were. And rerun this. Okay, so now we want to look at how well we did on power. So this one is that's our 1 kilowatt, just like we were shooting for. And if I look at the power here, it's 1.09. So you see that I'm at like a, like 90% efficient design. Okay, and let's look at where most of our power is going. So if I look right here, I have 27 watts. If I look right here, I have 60 watts. So you see that I'm now switching pretty well with my transistor that most of my power consumption is in the diode. So if I wanted to get this better, I need a smaller voltage drop across here, or switch the diode to another transistor with a small RDS on. Okay, so that's our first configuration. Our second configuration is using an NMOS and a bootstrap circuit. So now if I go through here, I'm going to redo this with a bootstrap circuit. I'm still going to need this NMOS, so I'll go ahead and leave that in. I'm going to need to get a different high power NMOS. Okay, so with this one, I need, again, the VDS to be 100, and I'm looking for one that has a small R on and a small gate charge, something that's kind of like a combination between the two. So if I go up here, oh, so these are looking pretty good. So here's one with 8 and like 40. Here's one that's 11 and 15. So any of these would probably be good. Let's just grab, oh, let's grab this one. No, let's grab this one. Looks pretty good right here. Okay, so now we need to build our bootstrap circuit. So if I go and review what my bootstrap circuit looks like, so here is my bootstrap circuit. So I'm going to have a small signal diode here, and then I have a capacitor that's connected between the source up through the capacitor, through the resistor over to the gate. So let's go ahead and build that. So we're going to grab a diode. And a capacitor. And then that is connected to the source down here. And then I have my resistor. And the resistor goes between the edge of the diode, and it's going to connect down to my transistor, and then this edge here connects over to the gate of my transistor, and make sure there's no connection point here. Okay, let's see how this works. Let's put in a small signal diode. So we'll use this 4148. Let's go ahead and leave this as 100 nano and use a 1K resistor there. Okay, let's see how this goes. Let's run it. So here is my signal here, and then you see that it's going to produce a gate voltage up here. You can kind of see that we're starting to roll off a little bit. And if I look at my gate to source, okay, running this, if I look at the gate, so the gate's going from 0 to 100, the source is going, sorry, the gate is going from 0 to 200, and the source is going from 0 to 100. So across my gate to source right here, I'm getting this voltage being applied directly across those two. Well, this voltage is 100 volts. That's too high. So we don't want the bootstrap to be taking the 100 volts and putting it across the gate to source. So we're going to need another voltage source in order to make that our 20 volts. So we're going to come in here and grab another voltage source over here. And we want a gate to source of 20 volts. So I'm going to put 20 volts there. And I'm going to cut this, so now the 20 volts is across my bootstrap, and then the 100 volts is over here. So now if I run this, you see this one's going up to the 120. So from the gate to the source, we're going from the 0 to the around the 20 volts. Okay, now you can see that this is starting to round a lot because I'm not getting enough current. So if I drop this resistor some, I'm going to consume more power over here, but I'm going to switch this faster. And so now it looks much squarer. And then I look over here, but now it's 70 volts. Well, why is it 70 volts? Well, if I look through here, this one is 25%. But then if I look right here, this one is 75. So this bootstrap is inverting. So I'm going to have to come in here and make this one 75 micro rather than 25 to take into account the inverting of my bootstrap circuit. And then if I look right here, 24, so it's a little bit low, and that's because if I look at the voltage here compared to the voltage there, you see I get a little bit of these lags caused by the transistor switching that I have to worry about. Okay, so if I come over here and I want this to be bigger, I'm going to come in here and I'm going to adjust this. So if I go down to 74, you see now I'm getting a little bit higher. Now I'm at 24.7. Let's just go up just a little bit more, or down a little bit more, and I go up a little bit more. And then I went too far. So let's go 0.5. And then I'm at the 25. And if I look at my peak to peak, okay, so here is my peak to peak. You see I'm at 2.6. I could adjust the inductor just a little bit if I wanted to get that right on. Okay, so now let's look at our powers. So again, here is my 1 kilowatt. Looks like it's not all the way steady state, but close. Oh. So I'm consuming the 54 watts there. And this one is 267. So you can see that this one isn't as efficient because the bootstrap circuit can't drive that as fast as my other driver. But I can't put that totem pole driver in here because I don't have my reference 120 volts. So I need to get a better driver. So in order to get a better driver, I need to buy a high side driver. So let's go look at high side drivers. So LTspice is a product from Analog. So if I go to analog.com, I can find one of their products, and the chances are their products are going to be available in LTspice. So if I go to products, and I'm going to go to power control, and oh, look, here's high side switches and MOSFET drivers. So these drivers are designed to be MOSFET drivers. And then we just have to see if these are included in LTspice. So you see these, chances are these new ones aren't in there, but let's go check and see. So if I grab a new component and it was an LTC and it was a 706. You see, they don't have the 7067, so they don't have those in yet because they're new products. So let's grab, oh, here's a 7,000 and a 7,001 and 7,000. Oh, these are 60 volt. We want the high voltage, so we want a 7,000 or a 7,001. So here's our 7,000, 7,001, and I just want the simplest one. You see, these ones have multiple connections to drive multiple MOSFETs. This one's simpler, so we're going to grab this one. So this is 7,001. Grab that in here. But we have to figure out how all of this works. So I'm going to have to go to here. We're doing the 7,001. And I'm going to see how this is connected up. So you see in this data sheet that we're going to ground all of these. We're going to put a capacitor between these 2 points. And then these 2 points are going to drive the high side, the gate of my high side transistor. And you see they're using an NMOS here. So we're going to go ahead and grab an NMOS. So this one is going to do our boosting. And so you see we have 2 voltage sources. This is the one that it's getting the boosting. And this is my supply that goes into the transistor. So I'm going to come over here and we are going to delete all of this. And we're going to go back to an NMOS configuration. But now we are more concerned about the R on. So I want a transistor with a fairly small R on and a fairly small gate charge. So again, I think we grab something like this one here. Okay, then we're going to delete all of this. And we're going to take this one and plug it in over here. But we're going to have to move some of this. Okay, so first of all, VCC, that goes over here to this one. Okay, these are the top gate up and down. So this is going to be pulling it up, this is going to be pulling it down. We have to connect both of these to the gate. Okay, let's give ourselves a little more room in here. Okay, and then go back and look at our sheet. And so you see that this VCC, UV, OV, LO, and the ground are all tied to ground. So we're going to go and tie all of those to ground. So that's all of these pieces over here. Here is our in. So I'm going to take this and wire it into my input. Okay, so then we go back and look at this. And this is the base, but we want to look at the data sheet, make sure we get all this right. And so there's this configuration, but when I looked at it before, if you look down on the bottom, they also have this block diagram showing here, which is kind of showing what's inside. And they also sometimes, you see they have this capacitor right here between the BST and the TS, so there's a capacitor here, and then they also put a diode between this input over to the BST. We're going to go ahead and put the diode in as well. So let's start with a 0.1 microfarad capacitor between BST and TS. Here's our Here's our BST, here's our TS. So we're going to put a capacitor right here. And they said 0.1 microfarad. Okay, and then they also had a diode between the BST and my VCC. And go ahead and grab a 4148, nice little signal diode. Okay, so now we have this whole thing. Let's run it and see what happens. The circuit was running really slow, and so I paused it because I had to try and figure out what the problem was. And the problem is, and lots of times if things are running really slow, it's usually because there's something that's supposed to be connected that isn't connected. And the problem is that this TS connection was supposed to be connected to the load, because remember, this is our Bootstrap Circuit piece. This BST stands for Bootstrap. So we forgot to make this connection over, or I forgot to make that connection over to the load. So what we need to do is, just to make it look nice, we will connect that over to here. And while we're at it, this was supposed to be 15 volts because that was the maximum that this gate driver can handle. So now we are ready to rerun this. And now it runs nice and fast. Okay, so if I look right here, here is the 25, 0 to 3.3 volts. And then over here, you see, oh, now this one isn't inverting. So because this one isn't inverting, now when I come over here, my voltage is going to be too high. And so I have to go back and change this to the non-inverting configuration, back to the 25. And go back to the 10 milli and the 9.5 milli. And run this. And then you see we're around this 25, and we're around the 25, and everything looks pretty good. We obviously have to change this a little bit to get it the right one. So we're going to go to 26.5, similar to what we had before. And here is our 24.8. And we have our peak to peak of 2.6, close to the 2.5. And so now if I look at this voltage compared to this voltage, you can see that that works pretty good. So you can see that switching really well. And you see it's taking this and it's converting it up to the 120 to take this 15 and do the bootstrap. So this is actually doing the bootstrap circuit for you, but being able to put out the high gate driver piece. And to look at the efficiencies really quick, or the powers, you see here is our 990, close to the 1 kilowatt. Let's see how much power we have in these two pieces. This one's only consuming 5 watts. This one's consuming the 60 watts. So you can kind of see that the majority of our power consumption is in the diode like we wanted. And if I wanted to make this more efficient, I would have to change this diode into a MOSFET to drop its voltage, because you can see that its on voltage is like 2 volts. So if I take 2 volts times that high current, I get fairly high power when the diode is conducting. And that is the end of these 3 different configurations.